Heat Conduction Equation. This chapter discusses the fundamental equation governing heat conduction inside materials. Heat conduction is understood as an energy transfer mechanism driven by temperature gradients. The approach is based on an energy balance applied to a small volume element. From this approach, the differential form of the heat conduction equation is derived. This equation becomes the foundation for both steady-state and transient analyses in various geometries.
Lesson Plan: Heat Transfer. The course structure is designed to build understanding from basic concepts to advanced applications. The sequence of topics covers conduction, convection, radiation, and heat exchangers. Each chapter is connected through the concepts of energy balance and heat transfer mechanisms. This approach helps develop a systematic and progressive understanding. With this flow, thermal system analysis can be performed in a consistent manner.
Learning Outcome. The learning outcomes focus on understanding multidimensional and time-dependent aspects of heat transfer. Students are expected to derive and simplify the heat conduction equation. Boundary and initial conditions are treated as essential parts of the modeling process. Solving one-dimensional problems becomes a core competency. The analysis also includes heat generation effects and temperature-dependent thermal conductivity. Heat transfer as a vector. Temperature is treated as a scalar quantity because it has magnitude but no direction. In contrast, heat flux is a vector quantity since it has both magnitude and direction. The direction of heat transfer is always from higher to lower temperature. Vector representation helps in understanding the path and intensity of energy flow. This concept is essential for multidimensional conduction analysis. Heat transfer direction. The direction of heat transfer is defined using a sign convention in the coordinate system. Heat flow in the positive axis direction is defined as positive. Conversely, heat flow in the negative direction is assigned a negative sign. This convention helps maintain consistency in writing energy equations. With this rule, the interpretation of calculation results becomes clearer.
Coordinate systems. The choice of coordinate system depends on the geometry of the object being analyzed. Cartesian coordinates are suitable for simple geometries, such as slabs or blocks. Cylindrical coordinates are used for pipes or cylindrical objects. Spherical coordinates are appropriate for spherical geometries. Selecting the proper system simplifies the derivation and solution of the equations.
This slide is a check your understanding question designed to test students' knowledge of cylindrical coordinates. It asks students to identify the third element in the cylindrical coordinate system, which combines radial distance, angle, and a third variable to describe cylindrical shapes like pipes. The blank in the sentence prompts students to recall and fill in the missing term, height, or z coordinate, to complete the definition of the system, r, phi, z. This interactive slide reinforces the concept of cylindrical coordinates and ensures students can apply their understanding to real-world shapes.
Steady and transient conditions. The difference between steady and transient conditions is shown through whether temperature changes with time. In steady conditions, the temperature distribution does not vary with time. In transient conditions, temperature changes with time until a steady state is reached. This difference also affects the heat transfer rate inside the material. This concept forms the basis for classifying heat conduction problems.
Steady versus transient heat conduction. No energy is stored within the system. The heat transfer rate is constant across the entire section. In transient conduction, energy can be stored or released, causing temperature to change with time. The temperature distribution in transient conditions is dynamic. This difference is very important in modeling real thermal systems.
Two-dimensional heat transfer. In two-dimensional heat transfer, temperature varies in two spatial directions. Heat flux has components along each of these directions.
Boundary conditions on each side strongly influence the temperature distribution pattern. Such problems often appear in bars or plates with specific geometries. Two-dimensional analysis provides a more realistic picture than one-dimensional analysis. One-dimensional heat transfer in windows. In many practical cases, heat transfer can be approximated as one-dimensional. An example is heat flow through a window, which is dominant perpendicular to the surface. The effect of heat transfer in other directions can be neglected because it is relatively small. This simplification makes the analysis much easier. Although simple, this approach is still sufficiently accurate for many engineering applications. The answer is C, perpendicular to its surface, with negligible effects in other directions. A, horizontally across the surface. Incorrect. Heat transfer through a window primarily occurs perpendicular to the surface, not horizontally, as the temperature gradient drives the flow in the normal direction. B, randomly in all directions. Incorrect. Heat transfer is not random, but directional, dictated by the temperature gradient, which is perpendicular to the window surface. D, in multiple directions, including the roof and sides. Incorrect. Heat transfer through the window is typically analyzed in one primary direction, perpendicular to its surface, with other directions considered negligible. The temperature gradient and heat flow. The temperature gradient represents the rate of change of temperature with respect to position. A negative sign in the gradient indicates that temperature decreases along a certain direction. The direction of heat flow is always opposite to the direction of increasing temperature. The steeper the temperature gradient, the higher the heat transfer rate. This concept forms the basis of Fourier's law of heat conduction. Heat transfer vector. The heat transfer vector is always perpendicular to isothermal lines. The direction of this vector shows the path of heat energy flow inside the medium. The magnitude of the vector represents the intensity of heat transfer per unit area. The vector can be decomposed into components along the x, y, and z directions. This vector representation simplifies three-dimensional heat conduction analysis. Heat generation in electric range. Heat is generated by converting electrical energy into thermal energy through electrical resistance. The heating elements become hot due to the electric current flowing through them. This thermal energy is then transferred to the cookware and the oven chamber. This process is an example of internal heat generation in a solid medium. Control systems are used to regulate the desired temperature level. Solar radiation heat absorption. Solar radiation absorbed by water is converted into internal thermal energy within the medium. The intensity of heat generation decreases with increasing depth. This happens because less radiation can penetrate into deeper layers of water. This phenomenon is important in the thermal analysis of water bodies and solar systems. The correct answer to complete the sentence is heat generation, which captures the idea that absorbed solar energy behaves like a distributed heat source in the water. 1D heat conduction in plane wall. Heat conduction analysis is performed on a thin volume element inside a plane wall. An energy balance is applied by considering heat entering, leaving, and being generated. The cross-sectional area is assumed constant to simplify the analysis. This approach is suitable for one-dimensional problems. From this, the basic heat conduction equation for a plane wall is obtained. Simplified 1D heat conduction. Under steady-state conditions, time-dependent terms are removed from the equation. If there is no internal heat generation, the equation becomes even simpler. This form leads to a linear temperature distribution as the solution. This result is often used in the analysis of simple walls. This simplification helps in understanding the basic behavior of heat conduction. 1D heat conduction in cylinder. In a cylinder, heat conduction occurs radially, toward or away from the center. The cross-sectional area for heat flow changes with radius. An energy balance is applied to a thin cylindrical element. This change in area causes the equation form to differ from that of a plain wall. This analysis is important for pipes, cables, and tubes. Differential forms for cylindrical heat conduction. The cylindrical heat conduction equation can be written in a form that is ready to be integrated. Another form can be obtained by expanding the derivatives with respect to radius. Both forms are mathematically equivalent. The assumption used is steady-state condition without internal heat generation. From this equation, the temperature distribution in the cylinder can be obtained.
1D heat conduction in sphere. In a sphere, heat flow also occurs radially, with surface area changing with radius. An energy balance is applied to a thin spherical element. The effect of internal heat generation can be included in the analysis. The rapid change in surface area influences the shape of the temperature distribution. This case is important for particles, fuel spheres, and spherical systems.
The answer is D. Radial heat conduction considers variations in surface area and can incorporate internal heat generation affecting temperature distribution. A. A cylindrical volume element is used to establish the energy balance for heat transfer. This is incorrect because radial heat conduction in a spherical shell specifically involves a spherical volume element, not a cylindrical one. Cylindrical volume elements are used for analyzing conduction in cylindrical geometries, such as pipes or rods. B. Heat transfer occurs uniformly without considering the geometry of the sphere. This is incorrect because radial heat conduction in a sphere inherently depends on the geometry, particularly the variation in surface area as the radius changes. Ignoring this would oversimplify the problem and lead to inaccurate results. C. Heat conduction is analyzed along a flat surface, ignoring variations in surface area. This is incorrect because the analysis of radial heat conduction in a sphere must consider the curved geometry and varying surface area of the spherical shell. Flat surface assumptions apply to planar geometries, not spherical ones. D. Radial heat conduction considers variations in surface area and can incorporate internal heat generation affecting temperature distribution. This is correct because it accurately captures the key aspects of radial heat conduction in a spherical shell, including the effects of geometry and internal heat generation. 3D heat conduction in volume element. Three-dimensional heat conduction involves energy flow in the X, Y, and Z directions. Each direction has its own heat flux component. An energy balance is applied to a small volume element inside the material. This equation can also include the effect of internal heat generation. This approach represents the most general form of the heat conduction equation. 3D to 1D heat conduction equation. The three-dimensional heat conduction equation can be simplified when temperature variation is significant in only one direction. The derivative terms in the other two directions can be eliminated. The result is a one-dimensional equation that is much easier to solve. This simplification often applies to plain walls, long cylinders, or spheres. This approach remains accurate as long as the dominant direction assumption is satisfied. Cylindrical volume element. A volume element in cylindrical coordinates is defined by small changes in radius, angle, and height. Its geometric shape follows the cylindrical coordinate system. This element is used as the basis for deriving the heat conduction equation. Each face of the element has a different area depending on its position. This approach is very important for the analysis of pipes and cylinders. Spherical volume element. A volume element in spherical coordinates is defined by small changes in radius, polar angle, and azimuthal angle. This shape represents a small segment of a sphere. This element is used to derive the heat conduction equation in spherical geometry. The surface area changes very rapidly with radius, This causes the equation form to differ from those of cylinders and plane walls.
General solution of differential equation always contains arbitrary constants. Without boundary conditions, there are infinitely many possible solutions. Boundary conditions are required to select the solution that matches the physical problem. Each heat conduction problem has its own unique boundary conditions. Therefore, a specific solution is obtained from the general solution.
The answer is boundary, because applying boundary conditions allows us to find the specific solution that fits the physical situation being modeled. This check reinforces the idea that without boundary conditions, differential equations have infinite general solutions, but when boundaries are applied, we can solve for unique, physically relevant results.
Boundary conditions for heat transfer. To determine a unique solution, two boundary conditions are required for a one-dimensional problem. These conditions can be specified temperatures or specified heat fluxes. The solution must satisfy all the given boundary conditions. Without proper boundary conditions, the solution has no physical meaning. Therefore, boundary conditions are an essential part of thermal modeling. Specified temperature boundaries. In this type, the temperature is specified exactly at both surfaces. The temperature distribution inside the material must adjust to these values. This type of problem is often called a Dirichlet boundary condition. Such conditions are commonly found in walls in contact with constant temperature reservoirs. The solution is usually relatively simple.
Specified heat flux boundaries. In this condition, the heat flux is specified at the surface rather than the temperature. The temperature gradient at the surface must adjust to match the given flux. This condition often appears on surfaces subjected to constant heating or cooling rates. Mathematically, this is called a Neumann boundary condition. The solution requires integration while carefully considering the temperature gradient.
Insulated wall boundary conditions. At an insulated surface, the heat flux is zero. This means that the temperature gradient at that surface is also zero. The other surface usually has a specified temperature or heat flux. This condition is often used to model walls with thick insulation layers. This approach simplifies the analysis because one side does not transfer heat. B. Insulation eliminates heat flux, resulting in a zero temperature gradient at the insulated surface. Explanation of incorrect answers. A. Incorrect. Insulation eliminates heat flux at one surface, so there is no constant heat flux across the wall. C. Incorrect. Specified temperature at one surface, not both, defines the boundary condition and does not result in uniform conduction across the wall. D. Incorrect. Insulation and specified temperature significantly affect the heat conduction behavior by defining boundary conditions.
Thermal symmetry boundary. In walls with symmetric geometry and boundary conditions, the temperature profile is also symmetric. At the center plane, there is no heat flow crossing the plane. This means the temperature gradient at the center is zero. By using symmetry, the computational domain can be reduced to half. This approach makes the solution of the problem more efficient.
Convection boundary conditions. In many real systems, heat is transferred by conduction inside the wall and by convection at the surface. The heat flux at the surface is determined by the temperature difference between the surface and the surrounding fluid. The convection heat transfer coefficient plays a crucial role in determining the magnitude of the flux. Both sides of the wall may have different convection conditions. This combination results in a mixed boundary condition involving conduction and convection. Direction of heat transfer. The mathematical form of the boundary condition does not change even if the direction of heat flow is different. Only the sign in the equation changes according to the direction convention. The relationship between conduction inside the wall and convection at the surface remains consistent.
Correct sign selection is very important to avoid misinterpretation. With proper conventions, the energy equations remain valid for any heat flow direction. Radiation boundary conditions. In addition to convection, surfaces can also exchange heat by radiation. Radiative heat transfer depends on surface emissivity and the difference in absolute temperatures. This mechanism is often significant at high temperatures. This boundary condition combines the effects of conduction inside the wall and radiation at the surface. The analysis becomes more complex because the radiation relationship is nonlinear with respect to temperature. Interface boundary conditions. For two materials in perfect contact, the temperature at the interface must be continuous. There must be no temperature jump at the contact point. The heat flux leaving the first material must equal the heat flux entering the second material. The thermal conductivity of each material affects the temperature distribution. This condition is very important in the analysis of layered walls or composite materials. The heat flux leaving one material equals the heat flux entering the other at the interface. Steps to solve heat transfer problems. The solution process starts by formulating the differential equation and its boundary conditions. After that, the general solution of the equation is obtained. The next step is applying the boundary conditions to determine the arbitrary constants. The final result is a specific solution that matches the physical problem. This sequence of steps helps maintain consistency and accuracy in the analysis. Solving second-order differential equations. A second-order differential equation is solved by integrating it twice. The first integration yields the first derivative with one arbitrary constant. The second integration gives the general solution with two arbitrary constants. This form is still general and not yet specific to a particular case. Boundary conditions are needed to complete the solution. Applying boundary conditions. Boundary values are substituted into the general solution to eliminate the arbitrary constants. Each boundary condition provides one additional equation. With two boundary conditions, the two constants can be determined. The final result is a solution that no longer contains unknown constants. This solution fully represents the physical system being analyzed. Boundary value solutions. If the boundary conditions are consistent, a unique solution will be obtained. If the boundary conditions are contradictory, no solution is possible. In some special cases, the boundary conditions may lead to multiple solutions. The existence or non-existence of a solution is entirely determined by the boundary conditions. Therefore, the choice of boundary conditions must always reflect the real physical situation. Inconsistent boundary conditions lead to no solution for the equation. Nonlinear equation solving. Some heat conduction equations are nonlinear and cannot be solved analytically in a direct manner. Numerical or iterative approaches are often used for such problems. The process starts by guessing an initial value for the unknown variable. This value is then gradually refined until convergence is achieved. This method ensures that the obtained solution is sufficiently accurate for engineering purposes. Steps. Cylindrical heat conduction. The solution starts by integrating the differential equation for the first time. The result is then simplified by dividing by the radius. After that, a second integration is performed to obtain the general solution. Each step follows strict mathematical rules. This procedure yields the temperature function in cylindrical coordinates. Heat transfer in spherical containers. Under steady-state conditions, the total heat transfer rate remains constant. However, the heat flux per unit area decreases as the radius increases. This happens because the surface area increases with radius. The same amount of energy must pass through a larger surface. As a result, the intensity of the heat flux becomes smaller. The answer is C. Heat flux decreases with increasing radius because the surface area increases, but the total heat transfer rate remains constant. Explanation of incorrect answers. A. Incorrect. Under steady-state conditions, the total heat transfer rate remains constant. It does not decrease with increasing radius. B. Incorrect. Heat flux does not remain constant. It decreases as the radius increases due to the increasing surface area. D. Incorrect. Surface area significantly affects heat intensity, as larger areas at outer radii spread the heat over a broader surface, reducing flux.
Heat generation in solids. Heat generation in solids can originate from various physical sources. Nuclear reactions, chemical reactions, and electrical heating are common examples. The generated energy must be transferred out to keep the system stable. Otherwise, the temperature will continue to rise. This phenomenon is very important in the design of nuclear fuels and heating elements.
Heat generation at steady state. Under steady-state conditions, the heat generated must equal the heat leaving the system. There is no accumulation of energy inside the material. The surface temperature is determined by the balance between heat generation and heat removal. This process involves conduction inside the material and convection at the surface. This balance ensures that the system remains in a thermally stable condition.
Heat flow in cylindrical shell. The heat generated inside a cylindrical shell must flow out through the surface. The amount of generated heat depends on the volume of the shell. All of this heat eventually leaves the system through the curved surface area. The temperature distribution inside the material is determined by this balance. This analysis is important for thick-walled pipes and heated cylindrical elements.
Maximum temperature in symmetric solids. In objects with symmetric geometry and uniform heat generation, the maximum temperature occurs at the center. This is due to the symmetry condition that forces the temperature gradient to be zero at the center. From the center toward the surface, the temperature decreases gradually. This pattern applies to walls, cylinders, and spheres. This concept is important for evaluating material temperature limits.
The maximum temperature occurs at the center due to symmetry.
Thermal symmetry in a wire. In a wire with uniform heat generation, symmetry applies at the center line. At this point, there is no heat flow crossing the center. The temperature gradient is zero at the wire center. The temperature increases from the center toward the surface. This pattern reflects the typical radial distribution in cylindrical conduction. Thermal conductivity trends. The value of thermal conductivity for each material depends on temperature and material type. In metals, thermal conductivity is generally high and slightly decreases as temperature increases. In nonmetals, the variation of conductivity with temperature can be very significant. Engineering materials, such as stainless steel, show more moderate changes. This behavior must be considered for accurate heat conduction analysis. Temperature variation in plane walls. If thermal conductivity is assumed constant, the temperature distribution in a wall is linear. If conductivity increases with temperature, the temperature profile becomes curved with a decreasing gradient. If conductivity decreases with temperature, the profile is also curved, but with an increasing gradient. These material property variations affect the shape of the heat conduction solution. Therefore, the assumption of constant conductivity must be used carefully. The answer is C. Engineering materials like stainless steel show gradual changes in thermal conductivity with temperature. Explanation of incorrect answers. A. Incorrect. Metals typically have high thermal conductivity, but it decreases slightly with increasing temperature, not increases significantly. B. Incorrect. Nonmetals have thermal conductivity that varies significantly with temperature, not remains constant. D. Incorrect. Different materials, metals, nonmetals, and references. All figures and main concepts in this chapter are based on the referenced heat transfer textbook. This reference provides the theoretical foundation and engineering application examples. The notation and analytical approach are consistent with that source. This ensures alignment with international standards in heat transfer education. This reference also serves as the main source for further in-depth study.